If you have been following the videos in order, you've just exited a set of videos which took you a little bit closer to the deep end of more abstract and conceptual mathematics, and it might have been a little bit weird for you, but it does have a payoff that returns us back to kind of our normal flow of topics in which everything that we do reduces to solving a system of linear equations. So the ideas that you saw in the last set of slides, like vector spaces and subspaces, are really crucial in the construction of solution sets to systems of linear equations and differential equations, which many of you might experience after you're done with this little course. The idea that you can have a collection of things, like solutions, that's special enough that if you take a couple of these things and add them together, for example, you create another one that's in the same set, that has the same property, that is, might still be a solution to your equations or your differential equation. And that idea is really important. So what we're going to do here is consider the idea of linear combinations of things, which means scalar multiples added up, and spanning sets, which you'll see in just a second. So we are going to go full circle. We started this class looking at systems of linear equations. We detoured a little bit, and now we're going to return right back again. So the two ideas again we're looking at are linear combinations of vectors and the span of a set of vectors. And once we learn what the span is, we're going to learn how to test if other things are in it. Linear combinations underlie everything that we're going to do from here on out. So a little bit more formally, a linear combination of a set of vectors like v1, v2, and so on through vn is what you get when you put together scalar multiples of the vectors all added up. That's a linear combination. So, example, here's three vectors listed out, v1, v2, and v3. And let's just say we do 3 times the first minus 2 times the second plus 1 times the third. Well, that's a linear combination of those three vectors. And simplified, that produces the vector 5, 8, 9. Notice that nothing unusual happened. We created a linear combination of vectors from R3, and we found another vector in R3. One of the themes you've seen repeatedly now is that we're using the word vector much more widely than you may have been used to using it before. It's not just about geometric pointy vectors with an arrowhead on them, but anything that belongs to a collection of like things that might be called a vector space can be called a vector. So polynomials, matrices, different kinds of functions, lots of stuff we've seen. We're going to apply the word vector to all of them, and that means we can also form linear combinations of other creatures, such as here is a linear combination of a pair of 2 by 2 matrices. So, building a linear combination of vectors is relatively easy. You just pick your vectors, slap scalar multiples on them, and then add up the result. And ta-da, there's a linear combination. That's easy in that forward direction. The reverse direction is a little bit tougher. Let's say you have a set of vectors and you're thinking about the linear combinations of them. Can you find out if this other particular vector is a linear combination of them? So you have one in mind and you're trying to decide, is this vector a linear combination of these others? Now, the collection of all the possible linear combinations of a set of vectors is called the span of that vector. So think of vectors as like mathematical Legos. So you have a collection of actual geometric vectors or polynomials or some kind of matrices. Think of them as Legos that you use to build other creatures that are like them. So if I have 3 matrices sitting here, I can make linear combinations of them and build new matrices. Just like you can take some Legos and put them together to build new Lego constructions, right? The set of everything you can make through those linear combinations is the span of that set of vectors. So when we collect our vectors, we put little wiggly brackets around them to indicate we've collected them together into a set. And asking this whether this new vector W can be written as a linear combination of those vectors in the set is the same thing as asking, is this vector W in the span of that set? And to shorten it up, the notation is span S with the S in squiggly brackets because S is a set of things, and so the squiggly brackets denotes that. So to just practice with that terminology, here are the two examples we saw earlier. A linear combination of vectors from R3 producing the vector 5, 8, 9, and a linear combination of two 2x2 matrices producing a third 2x2 matrix. And now we would say that that vector 5, 8, 9, since it was created as a linear combination of the other three vectors, is in the span of those three vectors. And the vector 1, 11, negative 3, 22. Let me move the mouse so that it actually looks like a negative 3. That vector is in the span of the other two because it was created as a linear combination of them. So, again, that forward part is easy. We built the vector 5, 8, 9 directly, so we know it's in the span of the other three that built it. If we pick a new vector, like negative 3, negative 4, 6, now we can ask, is this vector in the span of these three vectors too? In other words, is this vector negative 3, negative 4, 6 possibly written as a linear combination of the other three, just like 5, 8, 9 was? And to investigate this, here we go. We're going to generate a system of linear equations. And here's how that works out. If this new vector negative 3, negative 4, 6 is in the span of the vectors in question, then it gets written as a linear combination, which means there are coefficients of each of those vectors that, when you put together the linear combination, gives you the vector negative 3, negative 4, 6 that we're looking for. Now, the way you match the left side to the right side is by going through each of the components. So, for example, in order to produce that negative 3 in the first component on the right-hand side, you would add together 1a, negative 1b, and 0c, so just a minus b. To produce the negative 4 on the right-hand side, you would put together all the second components, such as 2a, 0b, and 2c, so 2a plus 2c, and then same for the third. So matching each of the components from left to right, you get three equations in three unknowns. And now there's some color coding there to help you track them. Let's bust out the component-wise showing of the vectors to just list what has to happen in each component individually. And there we go. Three equations, three unknowns. Now, having been through this route before, you know how to solve three equations and three unknowns, so we're not going to go through the details. We'll just leap right to the end. Although, just as a sample, as a reminder, here's how that could work. And let me pull in my friend, the Ziggy HD. Oh no, I've hidden my equations from myself. That's bad. Well, let's see what I can remember. Our equations are a minus b equals negative 3. And I'm going to cheat here. 2a plus 2c equals negative 4. Yes, I'm left-handed and I'm blocking your view while I'm writing. And then, over here, 3a plus b plus 2c equals 6. So there's our system of three equations in three unknowns. And the procedure to solve them begins with writing it in matrix format. So the first equation has coefficients of 1, negative 1, and 0. The second has components of 2, or coefficients of 2, 0, and 2. And for the third one, 3, 1, and 2. Like that. The unknowns are A, B, and C. And the right-hand side is negative 3, negative 4, and 6. And then from here you have a couple of choices. For example, we could solve for our unknowns A, B, and C by applying the inverse of the coefficient matrix. Like so. Of course, that only works if the inverse exists, right? And the other way to do it is to build the augmented coefficient matrix, which is 1, negative 1, 0, negative 3, 2, 0, 2, negative 4, 3, 1, 2, 6. My dog is excited about this. And then do Gaussian elimination to arrive at the solution. So you have a couple of different options about how to go through that, and frankly at this point you don't need to do it by hand anyway. You can use technology to assist you, but that was just a reminder of the processes that we've looked at already. And the net result for this example is that there are indeed those coefficients a, b, and c that will allow us to write the new vector -3, -4, 6 as a linear combination of the three given ones. And so we would say yes, the new vector is in the span of the three given vectors. And there's bonus information. You've used the word components for a lot of your life now, and that's, say, the component of a particular vector relative to the x, y, or z axis. That links in here because the vectors, say in 3 space, 1, 0, 0, 0, 1, 0, and 0, 0, 1, span all of 3 space. Any other vector can be written as a linear combination of them, and the components of a vector are the very coefficients that allow that to happen. Those three regular vectors, the 1, 0, 0, 0, 1, 0, and 0, 0, 1, are not the only trio of vectors that span all of R3. Well, not any, but there are other sets of 3 that do, like the ones currently at hand, for example. And so those coefficients that we discover that allow us to write this new vector as a linear combination of the other 3 are the components of that vector relative to the other 3. So let's go to a less comfortable scenario where we're dealing with polynomials. So here are 3 polynomials, P1, P2, and P3. And we're going to ask, is this other polynomial, 2x squared minus 3x plus 4, in the span of those 3 polynomials? Remember, polynomials can be considered as vectors now. If this new polynomial is in the span of P1, P2, and P3, then we say that that function, that new polynomial, can be written as a linear combination of them. That means we can find coefficients that will create this last vector as a linear combination of the other 3. The way we match the left side to the right side here is that we match the coefficients of x squared, x, and the constant. So if you trail along the left-hand side, the coefficients of x squared are a and c. The coefficients of x are a, 3b, and -2c, and so on. So again, color-coded. Here is the left side matched up against the right side, so the coefficients of x squared have to match. Those are in red. The coefficients of x have to match. Those are in blue. And the constants are in that purpley kind of thing. That produces 3 equations and 3 unknowns. That set does have a solution, and so, since it is possible to write f as a linear combination of the other 3 polynomials, it is in their span. And one more time, just with yet another scenario. This time it's matrices. So we're going to look at the list of matrices M1, M2, M3, and M4 and consider a linear combination of those 4 matrices and ask, can the matrix A be written as a linear combination of those other 4? In other words, is A in the span of the other 4? Here's how we set that up. So the left-hand side is A times M1 plus B times M2, etc. Then the right-hand side is the matrix that we're trying to see if we can create in this fashion. So if you match the upper left corners and the upper right corners and the lower left and the lower right, you will generate 4 equations and 4 unknowns so that you're making sure that each of the 4 spots match from left to right. Sadly, when you investigate this system, it will not have a solution, which means it is not possible to create that 2x2 matrix 0, 4, -2, 5 as a linear combination of the 4 matrices M1, M2, M3, M4. You can't do it. And that means this matrix A is not part of the span of those 4 matrices. Those 4 matrices will have a span, right? I mean, there are linear combinations of them, and you can consider what they all might be, but the other matrix that we're looking at, A, isn't one of them. So, a final note, when you're looking at problems like these, you're going to be in familiar ground. The new part is just the setup. Once you get to your system of equations, run with it, use a calculator, Maple, Wolfram Alpha, whatever you're comfortable with to get that stuff done, but don't lose the knowledge of how it works because you might not have that crutch when it's crunch time.